Integration by parts. One of the two main techniques of integration is integration by parts. Let u and v be functions of x, that is, u is a function in terms of x, and v is a function in terms of x. The derivative with respect to x of the product uv is du dx dot v plus u dot dv dx, or u prime v plus uv prime. This is the product rule. This equation implies that the antiderivative of uv is the right-hand side, which is uv equals the integral of du dx v dx plus u dv dx dx. If we isolate the integral of u dv dx dx, then we have uv minus the integral of du dx v dx. Letting du equals du dx dx and dv equals dv dx times dx, noted that we can treat these differential as fractions. The dx cancelled out. Then the integral of u dv equals uv minus the integral of v du. This is called integration by parts. This equation says that if we can rewrite the integral as the integral of u dv, then the answer is uv minus the integral of v du. This answer is not the final answer. We still need to evaluate the integral of v du. For example, evaluate the integral of x cosine of x dx. We're going to rewrite it at u dv, where u is x, therefore dv equals cosine of x dx. The integral is now in terms of u dv. That is, the integral of x cosine of x dx is now the integral of u dv. Integration by parts guarantee that the answer is going to be uv minus the integral of v du. But if u is x, then du is dx, and if dv is cosine of x dx, then v is sine of x. The answer is uv, which is x times sine x, minus the integral of v du, which is the integral of sine of x dx. X sine of x minus the antiderivative of sine of x is negative cosine of x plus c. How do we know that this is the answer? If we take the derivative of x sine of x plus cosine of x plus c with respect to x, we will end up with x cosine of x. Integration by parts guarantee that the integral of u dv is uv minus the integral of v du. The choice of u and dv's are important. Choose dv so that the antiderivative of dv can be easily evaluated. Similarly, choose u so that the derivative of u is simpler than u itself. We will know that we have a poor choice of u and dv if the integral on the right side is more complicated than the original integral. For example, evaluate the antiderivative of ln of x dx. In this case, it wouldn't make sense to let dv equals ln of x because we don't know what the antiderivative of ln of x is. So we let u be ln of x, then dv is the remaining part, which is simply dx. du over dx is 1 over x, or du is 1 over x dx. Since the derivative of v is 1, v is x. This integral is now rewritten at u dv, which guarantees that the answer is going to be uv minus the integral of v du. Note that we rewrite ln of x dx at u dv. But u is ln of x and v is x. v is x and du is 1 over x dx. Simplifying this, we have x times ln of x minus the integral of dx. The antiderivative of dx is x, so the answer is x ln of x minus x plus c. We can check this at the answer by taking the derivative with respect to x. Using the product rule, the derivative of x ln of x is 1 ln of x plus x times 1 over x. The derivative of x is 1 and the derivative of c is 0. Simplifying this, we have ln of x, and so x ln of x minus x plus c must be the antiderivative of ln of x. Integration by parts apply to definite integrals as well, using the fundamental theorem of calculus. The integral of u dv from x equal a to x equal b is uv minus the integral of v du, but we evaluate x equals a and x equals b. For example, evaluate the integral from 1 to 3 of ln of x dx. Using integration by parts, we know that the antiderivative of ln of x is x ln of x minus x. Evaluate 1 and 3 using the fundamental theorem of calculus. 3 ln of 3 minus 3 minus 1 ln of 1 minus 1. Simplifying this, we have 3 ln of 3 minus 2. This is the exact answer to the definite integral.